Testing, can you hear me? Testing again, can you hear me? Okay, testing one last time. All right, my video is public now, so I'm going to be learning about introductory statistics again. This time the topic will be discrete random variables. Uh, Let me just change to full screen. Okay, so last stream I was learning about probability topics. I read the entire thing, but it was mini revision for me. This stream I will be learning about discrete random variables. Um, yeah, I have my note, and like from the last time I learned, when I was learning it last time, I made some notes on proofs. So maybe this would help in this stream. So a random variable describes the outcomes of a statistical experiment in words. The values of a random variable can vary with each repetition of an experiment. Uppercase letters such as X or Y denote a random variable. Lowercase letters like X or Y denote the value of a random variable. X is a random variable, then X is written in words. If X, and X is given as a number. So capital X is the random variable. The lowercase is the actual value, right? For example, let capital X be the number of heads you get when you toss three fair coins. The sample space for the toss of three fair coins is this. Then small x is 0, 1, 2, 3. Capital X is in words and small x is in numbers. So capital X, the number of heads you get when you toss three fair coins. Notice that for this example, the x values are countable outcomes because you can count the possible values that capital X can take on and the outcomes are random. Capital X is a discrete random variable. A discrete probability distribution function has two characteristics. Each probability is between 0 and 1 inclusive. The sum of the probabilities is 1. So probability that x is equal to 0 is 2 over 50. Probability that x is 1 is 11 over 50. So what is this? At x, the number of times per week a newborn baby is crying wakes his mother after midnight. So so for 0 it's 2 mothers. For 5 it's 1 mother. Number of times per week a newborn baby is crying wakes its mother after midnight. I see. So only one mother wakes up at night 5 times. So capital X takes on the value 0, 1, 2, 3, 4, and 5. This is a discrete PDF because each Px is between 0 and 1 inclusive. The sum of the probabilities is 1. That is 2 over 50 plus 11 over 50 all the way till 1. Suppose Nancy has classes 3 days a week. She attends classes 3 days a week 80% of the time, 2 days 15% of the time, and 1 day 4% of the time, and no days 1% of the time. Suppose 1 week is randomly selected. Let x be the number of days Nancy attends her class. X takes on what values? Number of days Nancy attends her class per week. So what values can capital X take? So it can be 0.8 or 0.04 or 0 or 0.15. Suppose 1 week is randomly chosen. Construct a probability distribution table like one in example 4.1. Table should have two columns labeled X and PX. What does the PX column sum to? Well, it has to sum to 1, right? 0.8 plus 0 plus 0.04. No, wait. This is 0.01. 0.01 plus 0.04 plus 0.15 is 0.2. And then when we add it with 0.8, we get 1. Mean or expected value and standard deviation. The expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment over and over, you can expect this average. You toss a coin and record the result. What is the probability that the result is heads? If you flip a coin 2 times, does probability tell you that these flips will result in 1 heads or 1 tail? You might toss a fair coin 10 times and record 9 heads. As you learn in probability topics, probability does not describe the short-term results of an experiment. It gives us information about what can be expected in the long term. To demonstrate this, Carl Pearson once tossed a fair coin 24,000 times. He recorded the result of each toss. Raining heads 12 times. This experiment, Pearson illustrated the law of large numbers. The law of large numbers states that as the number of trials in the probability experiment increases, the difference between the theoretical probability of an event and the relative frequency approaches zero. When evaluating long term results of such statistical experiments, we often want to know the average outcome. This long term average is known as the mean or expected value of the experiment and is denoted by the Greek letter mu. In other words, after conducting many trials of an experiment, you would expect this average value. The mean mu of a discrete probability function is the expected value. So mu. Oh, I see. I see. So mu is what? Mu is for the population and sigma is the standard is sigma is the variance. Mu and sigma, they are both for the population, right? Not for the sample. So going back to the previous one, 80% of the time she will attend. So 3 days, 80% of the time. So if we do uh 3 days, actually let's do small. 3 days, 80% of the time. 2 days, 0.15%. 0.15, so 15%. 1 day, 0.01, was it? 0.04. And then this, right? So the average over here, the mean over here, we sum them with the relative frequency and then we get 3 times 0.8 plus 2 times 1 plus 2 times 0.15 plus 0.04. This is 0.8. So the mean is 2.47. When all outcomes in the probability distribution are equally likely, these formulas coincide with the mean and standard deviation of the set of possible outcomes. Suppose you play a game with a biased coin. You play each game by tossing the coin once. P heads, it's 2 over 3. P tails is 1 over 3. If you toss a head, you pay $6. If you toss a tail, you win $10. If you play this game many times, what will you come out ahead? Define a random variable x. So x is whether I get head or tail in one toss. If you play this game many times, okay, in one toss, and win, lose. So this is example 4.6. I just write 2.47. Example 4.6. Win, lose, and then we have, why did they write 10? So 10. Okay, so this capital X is the money you get after one toss. So 10, so X can be plus 10 or minus 6. Let me put this down a little bit. And then 1 over 3 for tails, 2 over 3 for heads. Why does this? Tails, heads, 1 over 3 for heads. Why does this say minus 12 over 3? 2 over 3. No, wait. Complete the following expected value table. No, 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 no. This is wrong. I think there's a probability that x is tails. Should I write small or big? You toss ahead, you pay $6. Toss ahead. And then um x times it with, I think this is it, right? So this times this is minus 12 over 3. This times this is 10 over 3. So the mu, how should I write mu? Is it written like this? It looks like m. Mu is this plus this. So you shouldn't play this game. On average, about 60. You lose on average about 67 cents each time you play the game. Like data, probability distributions have standard deviations. To calculate the standard deviation of a probability distribution, find each deviation from its expected value, square it, multiply it by probability, add the products, and take the square root. To understand how to do the calculation, look at the table for the number of days per week a men's soccer team plays soccer. To find the standard deviation, add the entries in the column labeled x minus mu square px. X is the actual value, right? So probability of 10. It's a probability of a win. I shouldn't write this. So we have this, and then we use this to calculate mu, and then x minus mu square times px will give us this. And then we add them and take the square root, right? That's a standard deviation. Yeah. Standard deviation is square root of 0.49, which is 0.7. Generally, for probability distributions, we use a calculator or computer to calculate mu and sigma. We reduce round off error. For some probability distribution, there are shortcut formulas for calculating mu and the sigma. Some of the more common discrete probability functions are binomial, geometric, hypergeometric, and Poisson. I don't know how to pronounce this one. A probability distribution function is a pattern. You try to fit a probability problem into a pattern or distribution in order to perform the necessary calculations. Okay. There are three characteristics of a binomial experiment. There are fixed number of trials. Think of trials as repetition of an experiment. The letter n denotes the number of trials. There are two possible outcomes, success or failure. The end trials are independent and are repeated using identical conditions. Because the end trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. Another way of saying this is that for each individual trial, the probability P for a success and the probability Q of a failure remain the same. For example, randomly guessing at a false statistics question has only two outcomes. The outcomes of a binomial experiment fit a binomial probability distribution. The random variable x is the number of successes obtained in the n independent trials. Okay. So I'll try to do what I remember. How do I draw a line? This is not what I want. How do I draw a straight line without any arrowhead? So whenever you do an experiment, the outcome of the experiment is either a success or a fail. Like tossing a coin, for example, either my frame rate's just dropped. So in a binomial experiment, in a binomial distribution, there is either a success or failure. Binomial distribution. Toss a coin, either heads or tail. So let's say you toss n number of times. You toss coin n times. N times. What is the probability of head or tail in terms of n? So if they were if n was 2, if n was 1, n was 1, then you can have head or tail. N is 2, you can have head tail or tail head. N is 3, you can have head 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 tail. Sorry, head tail head head tail tail, and then yeah, tail head head. Oh, this is going to be long. I'll just copy this. There. So the point. So how do we calculate how many? So this is a similar case to bit string. Remember in a discrete math we were learning about bit string. So bit string of length n would have a weight k depending on how many ones it has. So for example, this is 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. Wait. 1, 2, 3, 4, 5, 6, 7. Yeah. Uh 7 length bit string length 7 and wait 2. And we also said that the number of bit strings of length n, with weight k is n choose k. So the same thing will happen over here. If I have head, tail, head, head, tail, head, n times. No, wait. N times. Yeah. Now I remember. We can assign one of them to heads and another one to 1. So we can assign tails to 1 and heads to 0. So bit string of length n and weight k is n choose k. N choose k is number of k successes in n throws. If 0 is a fail and 1 is a success, number of k successes in n throws is n choose k. Right? If n is 3, if there are 3 throws, and let's say heads is success, how many times would I get one head? N choose 1. Well, 3 choose 1. Three, 1. 3 basically, right? So head is a success. So 1 over here, 2 over here, and 3 over here. There are 3 ways I can get 1 success and 3 throws. So binomial distribution says, so for 1 success, you have n choose 1. For 2 successes, we have n choose 2. For 3 success, we have n choose 3. Right? But I think a coin is a 50-50 example. I think a better example would be where the probability are different. Let's say probability of success is 0.9. Probability of fail is, let's say probability of success is 0.9. Probability of fail is 0.1. So I can have, so based on n, based on four trials, how many 1 success can I have? So 4 choose 1, right? I can have success, fail, 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 fails on 4 trials. How many times can I have once, or how many different ways can I have one success? Fail, 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 success. And yeah, I forgot this one. No, 4 different ways. So probability of one success, number of ways I can have one success from those 4 trials, times it by 0.9, times it by 0.1. So the reason I'm doing this is because the number of ways I can have one success. So 0.9 chance of success times it by 0.1 chance of fail and fail and fail. Or I can have, or I can have fail and then success and then fail and then fail. Or I can have this, or I can have this, right? And then 0.9. I forgot the middle one again. The point is there are 4 choose 1 ways of doing this. But since all the terms are same, we can just add them. Since there are 4 choose 1 way of doing this, we can just write 4 choose 1. Since this is repeated 3 times, you can just write it to the power of 3. 4 trials, 1 success, and 3 fails. So how about the probability of 5 throws with 2 success? So success, then success, and then the 3 fails. So success, success, fail, fail, fail. And there are 5 choose 2 ways of getting 2 successes and 3 fails. So what's the probability of 7 throws and 7 throws and let's say 1 success? So success, and then the rest 6 of the time fails, and then we have to add them 7 choose 1 times because there's 7 choose 1 different ways of happening. That's that's not the binomial yeah, I mean, yeah, that is the binomial distribution. The outcomes of a binomial distribution fit the binomial probability distribution. We ran a variable x, the number of successes obtained in the n independent trials, the mean mu and the variance sigma square for the binomial probability distribution are mu np and sigma square npq. Standard deviation sigma is root npq. Yeah, this is what I need this website for. Also, last stream I was asking why we use n-1 for sample variance instead of divided by n. I will link this article in this stream, and I think I will link into the previous stream. I think this explains why we use n-1 instead of n. Using n-1 instead of n is basically called Bézard's correction. I will drop the link below. I think in one of my previous streams as well. So x is binomial distributed. We represent it like this. Then probability that x is equal to x is equal to n choose x px 1 minus probability of success and then probability of failure. X is the number of successes. We can rewrite this as, okay, we can rewrite the above as this. So n factorial divided by x factorial n minus x factorial. This means that the formula for the expected value is basically the mean, is So so x times the probability of x, and we have to add it n times. Yeah. Instead of starting with x is equal to 0, we can start with x is equal to 1. Yep. Can also divide the first x. Divide the first x. Oh, yes, yes, yes. X divided by x factorial leaves us with x minus 1 factorial. Let's take np out. So np, and then this becomes n minus 1, and this becomes p to the power of x minus 1. This will allow us to rewrite our equation as this. Let m be n minus 1 and y be x minus 1. We are summing from x minus 1 till x to x equal 1 till n. But if we use y instead, then we are summing from 1 till n or 0 till m. Oh, and the sum of the probabilities is just 1. Use the binomial theorem. You get this. I mean, the sum of this part is just 1, right? So the expected value is just np. 0. What did I write here? Use the binomial theorem. Oh, yeah, yeah, yeah. We are writing this in this form. The binomial theorem is basically like uh, h plus k to the power of n. Actually, let's use another letter. The power of z would be z choose I 0 all the way till c. How many times we choose h? And then, yeah, this is basically the binomial theorem. This z looks like a 2. I'll just use another letter, b. Instead of k, it's 1 minus. Instead of k, if I write 1 minus h, the h and h cancels out and I'm left with 1. So this entire thing will be equal to 1. And then the expected value is n times p. As for the variance, we can use this equation, or this will be, we will learn this one later. The variance is e to the power of x square minus ex square. And then they get np times 1 minus p. I think I should add a link to this guy's video as well. This is where I got this proof from. So the notation is b and p. Read this as x is a random variable with a binomial distribution. Parameters n and p. Parameters are n and p. So n is the number of trials, p is the probability of success. Next, we have the geometric distribution. Wait, before I read the geometric one, I want to read the any experiment that has the characteristics 2 and 3 where n is equal to 1 is called a Bernoulli trial. Characteristics 2 and 3. Success and failure, and the trials are independent. Okay, that's called a Bernoulli trial. There are four main characteristics of a geometric experiment. A trial is repeated until a success occurs. Think of this as one or more Bernoulli trials with all failures except the last one, which is a success. In other words, if you keep repeating what you are doing until the first success. You keep repeating what you are doing until the first success, then you stop. Oh, I see, I see. So now it's geometric distribution. Uh, the geometric distribution is like success, success, success. Sorry, fail, 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 and then success. Fail, 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 and then success. The binomial distribution, we have a fixed n value. In a binomial distribution, we have a fixed n value, and then we want the number of ways to get a particular number of successes within those fixed n trials. In a geometric distribution, we want to figure out what n is. We want to figure out n, like we want to figure out probability of n. So let's say fail, probability of a fail 0.1, probability of a success 0.9. What is the probability that n is equal to 5? That is fail, 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 and then success. So in geometric distribution, the goal is to figure out the probability of n given that it's just fail, 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 and in the end there's a success. So this is to the power of 4 times it by 0.9. The repeated trials are independent. The probability p of a success and the probability q of a failure is the same for each trial. The random variable x represents the number of the trial in which the first success occurs. That is, x is the number of independent trials until the first success. The following additional attributes of the geometric distribution: the random variable is discrete. A random variable may be defined in two ways depending upon the analysis interest. In the example above, for throwing a die, or the question was what is the probability that the first success will be on the fifth throw? Alternatively, the question could be asked what is the probability that it takes 4 failures before a success? Implicit in the random variable is the probability of probability of success is constant. Therefore, so is the probability of failure. The geometric distribution is memoryless. There are very few probability distribution functions that are what is known as memoryless. And the geometric distribution is the only one with a discrete random variable that is memoryless. I forgot what memoryless meant. I think later they will tell us. Probability that x is more than t plus s, given that x is already more than s, is equal to probability that x is more than t. So probability that n is more than 5 would mean there has to be 4 failures, right? So q to the power of n minus 1. Probability. So the random variable x, what is it? What is the variable x? X is the number of trials, right? Let x be the number of games you play until you lose. Okay, okay. X is the number of trials. Just write x here. X is more than, and let's do k is the number of k failures, right? Actually, it's q to the power of a k, not minus one. The probability that x is more than 4, we need 4 failures for that. And probability that x is more than n given x is more than k is equal to q uh q n minus 1 time divided by p is more than n. No, not this, just n. I hate this. Divided by q to the power of k is equal to, what is the memoryless property? N plus k, number of previous failures. Um, oh wait, I did a mistake here. Let's do instead h plus k. Yeah, this is the memoryless property, right? Um, probability. I think there's a mistake here. I think they meant, oh no, they're talking about equal over here. Yeah, then equal is correct. Uh, okay. A safety engineer means that 35% of all industrial accidents in a plant are caused by failure of employees to follow instructions. They decide to look at the accident reports until they find one that shows an accident caused by failures of employees to follow instructions. On average, how many reports would the safety engineer expect to look at until they find a report showing an accident caused by the employee failure to follow instructions? So, 35% of all industrial accidents in the plant are caused by failures of employees to follow instructions. Did they talk about the expected value? The expected value is, so wait, I need to see an example. Okay, this is the right equation. Probability that x is equal to x. Failure x minus 1 times and then success in the end. So for one trial, it will be 0 failures. For 2 trials, it will be 1 failure. For 3 trials, it will be q square. So in summary, the expected value of x, which is the mean, is sum all the way till infinity I q I minus 1 p, right? P is a constant, right? But I forgot how you do this. I forgot how you do like a geometric and arithmetic in one. Um, we multiply both sides by 1 minus p. And then, okay, let's try that. So q, the expected value. And then I guess I can take the p out. So they said multiply by what? Multiply by q. Okay. I, q to the power of I, right? P is repeated, we can take p out. 1 minus p. So this minus this. So 1 minus p. So I mean 1p minus. Actually, let's do 2p minus 1p. 3p minus 2p. 4p minus 3p. And then, yeah, let's do that. Let's put this side. UXPI. And then E. Would it be easier to put the P inside? Let's think about this. Plus QP plus Q square P. Oh no, wait, I forgot. I uh, 1, 2, 3, 4, 5. P, sorry, Q, PQ plus 2 PQ square plus 3 PQ cubed plus P to the power of 4. And then we minus this. So we end up with P, P, and then 2 PQ minus PQ. 3 PQ square minus 2 PQ square. Um, 4 PQ cubed minus 3 PQ cubed. And this is E. And I can take the P out. 1 plus Q plus Q square plus. This is a geometric series with the Q as the thing, right? So in a geometric series, if you have 1 plus if you have if S is A plus AR plus AR square and R is less than 1 and more than 0, then S is equal to 1 minus R, right? So then this will be 1 over 1 minus Q, 1 minus Q. Because there's 1 minus Q over here, we have the square. Is that correct? No, that is not. No, yeah, it is correct actually. 1 minus Q is P. 1 over P. The variance. Oh my god. I use derivatives here. Is it the same guy? No, I don't think it's from. Is it from JB Statistics? I can't remember. Okay. Yeah, the thing. Expected value mean of this distribution. The expected value is 1 over p. This tells us how many failed tries to expect until we get the first success. This count includes in the count trials the trials that result in success. The above formula form of the geometric distribution is used for modeling the number of trials until the first success. The number of trials include the one that is a success. Access all the trials including the one that is a success. Okay. Standard deviation is 1 over p, 1 over p minus 1. 1 over p, 1 over p, 1 over p minus 1. Yeah, the variance matches. Case 2, random variable x is the number of failures before a success. In this case, the mean is 1 over p. The variance is wait, the variance is also 1 over p. Anyways, going back to the other question again. So, what they were asking. What is the probability that the safety engineer will have to examine at least 3 reports until they find a report showing an accident caused by employee failure to follow the instructions? There's a 35% chance of that, right? What is the probability? On average, how many reports would the safety engineer expect to look at until they found a report showing an accident caused by the employee failure to follow the instructions? So 35% of success. 1 over 35. Sorry, no, 1 over 35. No, 0.35. 2. So I'm expecting 8. I am expecting 3. Now that the mean does not mean a whole number, although the random variable is discrete and must be a counting number. What is the probability that the safety engineer will have to examine at least 3 reports? So what were the question they were asking? Will have to examine at least 3 reports until they find a report showing an accident caused by employee failure to follow instruction. 35% chance of success. What is the probability that the safety engineer will have to examine at least 3 reports until they find a report showing an accident? At least 3. So failure 3 times, right? Failure 3 times. Where's the answer? Yeah, I don't know. I wanted them to get the answer. Yes. Well, the lifetime risk of developing cancer is about 1 in 67. Let X be the number of people you ask until one says they have cancer. Let X is a discrete random variable with a geometric distribution. So we define geometric distribution like this, right? So GP. But the thing is this the case 1 or case 2? Also, I need to write the expected and variance for case 2 as well. What is the probability uh, of that you ask 10 people before one says they have cancer? 10 people. The probability of success is 0.015. Probability of failure is minus that. And they said 10 people, right? 10 people. Ask exactly 10 people. X is equal to 10, so 0. Oh no, 0.12, 0.131. How? I'm confused by the wording. Does this mean you ask 10 people and then all of them say they don't, and then the next one you ask, he says he does? You ask 10 people before one says they have cancer, right? X is equal to 10. It's not 0.0131. This is 131. No, no, I made a mistake. It should be 9. Wait, no. Actually, no. It should be 10. So 10 people say they don't, and then the next one you ask, he says he does. So it should be this 0.129. What is the probability that you must ask 20 people? Okay, for 20 it makes sense. I have to ask 20 people, so 19 for failure and 1 success, 0.113. Then the mean is 66.67. So what, on average I'm asking 66 people. Standard deviation is, keep forgetting the formula. 1 over p. I think the other formula made sense. 1 over p upon p square. Okay, hypergeometric distribution. There are 5 characteristics. You take samples from 2 groups. You're concerned with a group of interest called the first group. You sample without replacement from the combined group. For example, you want to choose a softball team from a combined group of 11 men and 13 women. Do I have anything on hypergeometric? No, I don't. Um, Team consists of 10 players. Take samples from 2 groups. Concerned with a group of interest called the first group. 11 men and 13 women. Each pick is not independent and sampling is done without replacement. In the softball example, the probability of picking a woman versus 13 over 24. Probability of picking a man second is 11 over 23 if a woman is picked first, 10 over 23 if a man is picked first. You're not dealing with Bernoulli trials. The outcomes of a hypergeometric experiment fit a hypergeometric probability. The random variable x is the number of items from the group of interest. Okay, so we are randomly choosing from men and women. So how many we end up choosing from men? Let's say the group of interest is men. How many do we end up choosing from men? A candy dish contains 100 jelly beans and 80 gumdrops. 50 candies are picked at random. What is the probability that 35 of the 50 are gumdrops? Candy dish contains 100 jellies and 80 gumdrops. 50 candies are picked at random. What is the probability that 35 of the 50 are gumdrops? 35 of the 50 are gumdrops. What is the probability of 35 of the 50 being gumdrop? Mm, jelly bean gumdrop 180. I don't think I'm familiar with this one. Jelly bean gumdrop 80 over 180. 100 over 180. If you do pick one, so 80 from here, then 79% chance picking gumdrop. There are still 100 remaining. 99. 100 over 180. So now, if I pick jelly bean, then there are 99 remaining. Why are there? No, this should be 100. And there are 80 jelly beans. Let me think this through. Okay, let's draw one more tree actually. Jelly, gumdrop, jelly, gumdrop. So I picked three candies, right? 80, 79, 78. 80, 79, 79 still remains. 100 over 178 chance. 80, 100. There's 79. Chance 178. 80, 100. I pick a jelly bean, so 99 jelly beans. 100. I pick a jelly bean. I pick a gum. 79. 100. 99. Jelly, jelly, jelly. 98. Jelly, jelly. Gumdrop. Gumdrop is still 80. This is 1. So let's say what is the probability of 3 gummies? 80, 79, 78. So what I'm noticing is that the numerator is subtracting by 1 and the denominator is subtracting by 1. What is the probability of 2 gummies? So gummy, jelly, gummy. Gummy, gummy, jelly. So numerator subtracts by 1. 80, 79, 100. So the gummy gummy jelly case, it's 80, 79, and then 100. Yeah. In the gummy jelly, gummy case, gummy jelly, gummy case, 80, 100, 79. So we know that gummy will drop by 2, right? So 80 will then turn to 79, 80, 100, 79. And then, okay, there is a pattern I'm seeing because the denominator decreases by 1. The numerator in all of the cases remain the same. Jelly, gummy, gummy, 100, 80, 79. So the numerator remains the same. If I'm asking for one success, group of interests, let's say jelly, if I'm asking for one success and three probability that jelly probability 3 jelly in sorry 1 jelly in 3 candies. So 3 choose 1 because that's the number of arrangements for this. And then we have the numerator decreasing by 1 every time. So the total, let's say it's n, and then n minus 1, and then n minus 2. And let's say I is the initial probability. So initial probability of gummy, and then uh, um, initial probability of gummy minus 1. And then the initial probability of jelly. I think this should be the general formula, right? Yeah, I think I can imagine that. So if it's 50 and they're asking for what? 35 of the 50 are gumdrops. So probability that 15 jelly, 15 jelly. In what? In 50 candy. 50 candies. 50. Choose 15. There are how many? There are 180 candies. 180 times it by 179. all the way till all the way till I need 50 of them, right? 180 minus 50. Is that correct? I'm getting 130. Is 130 included? This is the first. Okay, let's say the first candy is 130 first. Second candy is 130 second. 132. The third candy is 133. The 10th candy is 140. 20th candy is 150. 30th is no. I think this should be removed. Still 131. And we need the initial probability. Initial probability of picking jelly beans, which is 100 over 180. This minus 1 and then minus 2 and then minus 3 all the way till 15, right? All the way till 15. No, no. Minus 1. Yes. So from 0. Not not 0. From 0, yeah. From 0 to 14. Probability of picking a jelly is this. So this times it by this minus I. Minus I. So 100 over 180 and then 99 over 1. Wait, 99. Number of jellies should just be 100. 100 jellies and then 99 jellies and then 98 all the way to 100 minus 14. Thirty-four. How many gummies are there? 80. I don't even know if I'm doing this right. So 35 gummies. So it could be we choose one of the 80 gummies or we choose one of the 79 and then we choose one of the 74. Is this right? What is the probability statement? This 35. RBN, read this as X is a random variable with hypergeometric distribution. The parameters are R, B, and N. R the size of the group of interest, first group. So R in our, well, for me it was the jelly beans. So R size was 100. B size of the second group 80, and then N size of the chosen. Wait, what size? Okay, N size of the chosen sample. Size of the in this case it was 50 candies. Formula for the mean is n r over r plus b. A school site committee is to be chosen randomly from 6 men and 5 women. The committee consists of 4 members chosen randomly. What is the probability that 2 of them are men? How many men do you expect to be on the committee? 6 men and 5 women. And we are choosing 4 randomly, right? 4 times 2 times 3, 4 randomly. 6 plus 5 is 11. Probability of men. What is the probability that 2 of them are men? How many men do you expect to be on the committee? What is this? A probability that 0 men, probability of 1. Why is 0 a little bit up? You can still choose 5 women, right? Oh, yeah, yeah, that makes sense. Probability of all 4 of them being men. Okay. Poisson distribution. The two main characteristics of a Poisson experiment. The Poisson probability distribution gives the probability of a number of events occurring in a fixed interval time or space. If these events happen with a known average rate independently of the time since the last event. For example, a book editor might be interested in the number of words spelled incorrectly in a particular book. It might be that on average there are 5 words spelled incorrectly in 100 pages. The interval is 100 pages. So Poisson distribution. You spell it like this. Poison. Now, so in a Poisson distribution, uh, mu is known. I'll just type it. Mu is known. Mean is known. Now, given the mean is known, we have a particular time. The mean, let's say the probability of this light bulb randomly blinking, and the mu is let's say it blinks twice per minute. Uh, Number of events occurring in a fixed time interval or space. So 2 per minute. So the question is within X minutes, within a particular time, let's say 0 to 351 seconds, within this time, how many times light blinks, bulb blinks? Bank expects to receive 6 bad checks per day on average. What is the probability of the bank getting fewer than 5 bad checks on any given day? Of interest is the number of checks the bank receives in one day. So the time interval of interest is 1 day. Let x the number of bad checks the bank receives in one day. If the bank expects to receive 6 bad checks per day, then the average is 6 checks per day. Write a mathematical statement. Probability that x is less than 5. You notice that a news reporter says, on average, 2 times per broadcast. What is the probability that the news reporter says, more than 2 times per broadcast? Uh, so the average is given. Interval of interest, one broadcast, right? Number of average number of times a news reporter says during one broadcast is 2. Let x be the number of, what do you call this filler word? Uh, per broadcast. So per broadcast. Probability question is p x more than 2. Notation is like this. Probability mu. But sometimes people use lambda. Are they going to give us the formula? They gave it in the example. So the formula is Poisson distribution is discrete and thus more than 1 includes all whole numbers through infinity. The solution is to subtract the probability less than 1 and thus 1 minus px is equal to 0 plus px is equal to 1. What? So, um, what is the probability that Leah receives more than one call in the next 15 minutes? So probability of 0 plus probability of 1. 1 minus that will give you a probability of more than 1. Okay. Did they give us this formula before or did I miss it? No, they didn't, right? So probability is mu to the power of x e to the power of mu over x factorial. Okay, before I go there, so this article derives this equation. So this article here derives this equation, but it basically starts with the binomial distribution and it fixes the average but puts n to infinity. Let's say the probability of success is p. There are 1000 tries. We can apply the binomial distribution here. It gives the number of successes. So for n trials, probability p success, p x is equal to k gives us this probability. Now what we are going to do is we are going to fix the mean. So mean will remain np and we are going to take n all the way till infinity. First, we know what the mu is, but we don't know anything about p and n except p is very small and n is very large. Then we can have a model with mu as the only. And can we have a model with mu as the only parameter? Let's create a new probability function Pn by expanding a binomial probability function. So Pn, we have, yeah, n factorial by definition of combination, Pk, um, Oh yeah, and this I separated this. So 1 minus p to the power of n times 1 minus p to the power of minus k. I think the brackets make it more confusing. Let's get rid of the p. P to the power of k. Get rid of p. Okay. So we are writing p in terms of mu. Right? If n is very large, then the last term would be very close to 1. So this, yeah, this would make sense. N is very large. 1 minus mu to the power of n. Mu is fixed. 1 minus mean to the power of n. Sorry, divided by n. We're getting closer and closer to 1. That makes sense. This article represent e to the power of x as a limit, and that representation could be used here. So over here, e to the power of x, e to the power of x. My internet is fluctuating. So e to the power of x is 1 plus x divided by k to the power of k. This taken all the way till infinity. So if we have this term over here, n, if we make n larger and larger and larger, right, then this will become e to the power of minus mu. The terms after n minus k plus 1 can be cancelled out. Okay, this can be rewritten as this. I will switch k factorial and n to the power of k. Okay, so n from here will switch with k factorial. So n to the power of k divided and k factorial over here. Since there are k factor, since there are k factor in it, k factors in both the numerator and denominator. So k factors over here. Uh, then k factors over here, right? How are there k factors on top? Wait. Okay, that makes actually yeah, that's true. If n approaches infinity, all of these factors will get closer to 1. N divided by n is 1. I mean the denominator is larger, right? Denominator is larger. So this will be less than 1, this will be less, all the terms will be 1 or less. So n gets greater and greater. Yeah, it will get closer and closer to 1. So for very large n, you can write 1 mu to the power of k divided by k factorial e to the power of minus mu. Therefore, when n is very large and p is very small, the probability function is this. My internet got. Okay, wait. So as I was saying, where n, therefore, when n is very large and p is very small, the probability function is this. Sum the probability, does it add up to 1? It in fact does. If the variance of a binomial distribution is np1 minus p, then the variance of a Poisson distribution would be, so np is mu, and then the variance is mu. Yeah, that makes sense. So now I understand why mu to the power of x e to the power of minus mu to the divided by x factorial. I'll put the link in the art in the below the stream. This is just an exercise. Okay, I think I've been streaming for almost 2 hours. The next two are just exercises. So I will just end the stream here. And yeah, I will see you guys next time. Bye.